Hey everyone, and welcome back to The Explainer. Today, we're unpacking a project that is literally the backbone of modern software engineering. We are going to deconstruct how to build a scalable, event-driven products catalog microservice, totally from scratch. Specifically, we're looking at a product catalog system that asynchronously updates a search index. If you're a fan of clean architecture, decoupled systems, and just seeing exactly how data flows securely from point A to point B, well, you're in the right place. Let's get right into it.
So let's start with a fundamental question. Picture this. A massive e-commerce platform drops a huge flash sale, or a merchant updates the price of a super popular pair of wireless earbuds. How does that information immediately show up on the mobile app, the website, and the search engine all at the exact same time, without bringing the entire system to a grinding halt? The core challenge here is scaling distributed data systems effectively. If every single component relies on one giant database trying to update all at once, you're looking at a massive system-wide crash just waiting to happen.
So here's our game plan for today. We'll start with the e-commerce bottleneck, then unlock event-driven architecture. From there, we'll look at the producer service, RabbitMQ message brokering, the consumer service, and finally wrap up with innopotency and error recovery. All right, part one, the e-commerce bottleneck. Okay, think about a traditional synchronous update for a second. Your main API receives a product update. In a synchronous flow, that API tells the database to update, then it tells the search engine to update, then it tells the mobile backend to update, and it literally has to wait for every single one of them to say done before it can actually finish its job. These systems are just so tightly coupled. If the search engine is acting sluggish today, the whole system is sluggish. It causes massive bottlenecks and risks data inconsistency. But with asynchronous updates, which is the absolute heart of event-driven architecture, components are decoupled, the system is highly available, and we achieve what we call eventual consistency. The services aren't waiting around for each other, they just react to events in real time. Moving on to part two, event-driven architecture unlocked. So, what's actually under the hood making this decoupling possible? For our producer and consumer services, we're using Python with the FastAPI framework. It's fast, it's modern, and it's absolutely perfect for building out RESTful API endpoints. For our central nervous system, the message broker, we're utilizing RabbitMQ via the Pika library. For our authoritative data persistence, we're going with a robust MySQL database managed through the Alchemy's ORM. And crucially, for orchestration, we're wrapping this entire thing, the producer, consumer, RabbitMQ, and MySQL services, into individual containers managed by Docker Compose. This ensures our entire development and evaluation environment is totally consistent and super seamless to spin up. Oh, and a quick scope check before we go any further. You'll probably notice we're intentionally skipping API key authentication for this build. Obviously, in a real production environment, you'd absolutely secure your endpoints. But to maintain a laser focus on the pure mechanics of event-driven architecture, and honestly just to avoid scope creep, we're keeping our architecture clean of authentication today. That brings us to part three, the producer service. Let's actually follow the data by tracing a single payload. Our producer service exposes a specific endpoint, a post request to API/products/events. Let's say a merchant creates a new pair of wireless earbuds for $129.99. Step 1, the producer receives this JSON payload, simulating a product created event. Step 2, it validates that request against predefined schemas to make sure we actually have the required fields, like the product ID and the price. Step 3 is critical. The producer enriches this payload. It tags it with a unique event ID and a timestamp. And then step 4, it securely publishes this enriched, validated message right over to our RabbitMQ exchange. It does all of this incredibly fast, returning a success code to the user pretty much instantly.
Which leads perfectly into part 4, RabbitMQ message brokering.
I love to think of RabbitMQ like a busy corporate mailroom. When you need to send a super important package, you don't drive across the country to hand deliver it to someone's desk. You'd get zero actual work done if you did that. You drop it off at the mailroom and immediately go back to your desk. That's exactly what our producer service does. It drops the product created event into the RabbitMQ queue and goes right back to accepting new API requests. It doesn't know, and frankly, it doesn't care how long it takes for the database to save the product or for the search index to update. This decoupling right here is the absolute secret to high throughput scalability. All right, part 5, the consumer service. Meanwhile, our consumer service is running a background task, totally independent of the producer. Step 1, it continuously listens to that RabbitMQ queue, pulling down messages as they arrive. When it pulls our wireless earbuds event, it deserializes it. Step 2, it connects to our authoritative MySQL database and updates the products table. If it's a product created event, bam, it inserts a new row. If it's a product updated or product deleted event, it updates or logically deactivates that existing record. Finally, step 3, it asynchronously updates a local search index so users can actually find this brand new product. Actually, I want to pause on this quote for a second because it highlights a brilliant architectural design constraint. It says the search index will be implemented as a simple in-memory Python dictionary to fulfill requirements without adding a complex search engine like Elasticsearch. This is such a smart, lightweight choice for the scope of this project. By storing denormalized product data in a simple Python dictionary right inside the consumer service, our GET endpoint can execute basic keyword matching instantly. It perfectly demonstrates the concept of a separate read-optimized index, completely without bogging down our containerized environment with heavy software bloat.
And finally, Part 6, Idempotency and Error Recovery. Okay, we absolutely have to talk about idempotency. Basically, this means that processing the exact same event multiple times yields the exact same result, which prevents incorrect state changes or data corruption. Think about it. What if our consumer pulls the earbud event, saves it to MySQL, but then the network glitches out before it can tell RabbitMQ, hey, I'm done? RabbitMQ is gonna assume the message failed and just send it again. If we aren't careful, we end up with duplicate earbud entries or totally corrupted search data. We solve this by having our consumer track processed event underscore IDs in a small, dedicated MySQL table. Before processing any message, it checks this table. If it's seen the event underscore ID before, it just says nope and safely ignores the duplicate message.
But, we still need an ultimate safety net for when things truly go wrong. Even with idempotency, what if the MySQL database is temporarily down and the message absolutely cannot be processed? Well, first, robust error handling in the consumer catches the failure. Second, configurable retries kick in. The system will try to reprocess the event at least 3 times. But if it continually fails, we don't just drop the data. The unprocessable message is automatically routed to a dead letter queue, or DLQ in RabbitMQ. This means a failed event is never truly lost. It just sits safely in the DLQ, waiting for manual developer inspection, allowing us to fix the bug and replay the message later. Combine this with unit and integration testing aiming for over 70% coverage, and you've got yourself an incredibly resilient architecture. So we've seen how Docker Compose orchestrates our environment, how FastAPI and RabbitMQ enable asynchronous communication, and how idempotency and a dead letter queue protect our data integrity. It's a really powerful setup. So I'll leave you with this question to think about. If your system can survive localized failures without losing a single event, what other monolithic bottlenecks are you ready to decouple next? Thank you so much for joining me on this explainer. Keep building robust systems, and I will see you in the next one.